Math 8, Unit 6, Pythagorean Theorem in Real Numbers. Lesson 6, Introduction to Simplifying Radical Expressions. In this lesson, we will learn how to simplify radical expressions. But first, I encourage you to try these out on your calculator, or you can just see what happens here. If you do the square root of 54 on a calculator, if your calculator displays 9 digits, then it'll show this on the display, 7.348469228. Now, if you then check 3 square roots of 6, you'll find that it's the same number. Same thing happens with square root of 72 compared to 6 square roots of 2. So these expressions, although they look different, end up being equivalent to one another. Now, what we will be doing in today's this lesson is showing you how you will take an expression like square root 54 and change it to 3 square roots of 6. So in this video, I can reduce or simplify radical expressions. First, a little bit of vocabulary. A radical expression is an expression that contains a square root, or cube root, fourth root, or any other root, such as the square root of 2gm over r. That's an example of a radical expression. A radicand, the expression under the radical sign. By the way, a radicand, if you have the square root of 2x, 2x is the radicand. So, a radicand, the expression under the square root sign, the radical sign, is in simplest form if it contains no perfect square factors other than 1. And we'll be demonstrating what that means. The product property of radicals says that for any numbers a and b, where a and b are not negative, so they're greater than or equal to 0, the square root of the product ab is equal to the product of each square root. So I can take a and b and multiply them together, then square root them, or I can square root them first and then multiply them together. As a numerical example, the square root of 4 times 25, I could multiply them together first, or I could square root them first and then multiply. Either way, I do get 10. Okay, first example. I'm going to demonstrate these with 2 methods. Method 1, that many students tend to like better, is to do the factor tree on these. 27 goes into 3 and 9. 3 is prime. 9 can go into a couple of 3's. So the square root of 27 is the square root of 3 times 3 times 3. And the definition of square root, it's one of 2 equal factors of a number. So it takes 2 factors of a number to create a square root. So we take these 2 factors, 3 times 3, which happens to be 9, the square root of which is 3. We can take 2 factors from the inside, and it allows it to escape the square root, the radical sign, and become on the outside. Since I've got a 3 left over on the inside, that is my that's what's left as my radicand. That's method 1. Method 2 is to think in terms of squares. The perfect squares, 1, 4, 9, 16, 25, etc. You're going to factor your square root into squares and non-squares. So 9 is a square, and 3 is a non-square. So this is the square root of 9 times the square root of 3. The square root of 9 is 3, and the square root of 3 will not reduce. We end up getting the same answer here. It's just a different method. The blue method here ends up being faster most of the time, but it does require you to be able to factor out squares rather than do prime factorization. Let's look at the next example. Square root 150. 150 is 15 times 10. 10, of course, is 2 and 5, which are prime. And 15 is 3 and 5, both of which are prime. So the square root of 150 is the square root of 2 times 3 times 5 times 5. Now I can pull out a pair of 5's because the square root of 25 is 5. And at this point, I'm going to re-multiply these together. There's no pairs left. So I get 5 square roots of 6 as the answer here. Using the method 2, I can split up the square root of 150 into 25 times 6. So the square root of 25 times the square root of 6, which is 5 times the square root of 6. Same answer, different method. So method 1, the steps here, you're going to factor the radicand into prime factors. So you do your factor tree. You're going to remove factor pairs. 2 factors on the inside become 1 on the outside. Then you remultiply the factors left inside and the factors removed. Method 2, which is the fast way, sometimes. You're going to factor the radicand into squares and non-squares. Separate squares into separate radicals and evaluate each square root. Multiply all the whole numbers together that are on the outside and all factors left inside the radicand. So I'm going to demonstrate these 3 problems both ways. Method 1, 20 is 4 times 5. 5 is prime. 4 reduces down to 2 times 2, which are both prime, giving us the square root of 20 being the square root of 2 times 2 times 5. We can pull out a 2 that comes to the outside, and 5 is left on the inside. There's nothing to remultiply, so that is our answer. Method 2, you're going to split square root of 20 into the square root of 4 times the square root of 5. The square root of 4 is 2, so we get 2 square roots of 5. Okay, example 2, square root 52. 52 is 4 times 13. 13 is prime. 4 is 2 times 2. We are doing the square root of 2 times 2 times 13. The 2's can come out, and the 13 remains inside, giving us 2 square roots of 13. Method 2. The square root of 52 is equal to the square root of 4 times the square root of 13. The square root of 4 is 2. The square root of 13 does not reduce. We get 2 times the square root of 13. Example 3. 2 square roots of 32. First, factor down the 32. 8 times 4. The 4 can reduce to a couple of 2's, which are both prime. The 8 reduces to a 4 and a 2. The 2 is prime. The 4 can go down a little further, giving us more 2's. We have 5 2's here. So 2 times the square root of 32 is going to be 2 times 2 times 2 times 2 times 2. Kind of running out of room there. Now, I recommend copying down what we already have outside, then start pulling. We can pull the 2. We can pull another 2. And we do have a 2 left over on the inside that stays there. This might bring up the question, what happens if there's nothing left on the inside? And I'll go over that in a moment. 2 times 2 times 2 is 8. So we get 8 square roots of 2 here. Now for method 2. For 2 square roots of 32, 32 is 16 times 2, 16 being a perfect square. So this is 2 times 4 times the square root of 2. I remultiply the whole numbers together, and I get 8 square roots of 2. Okay, so what happens if when we are square rooting, we get rid of the everything that's inside? So the square root of 100, which by the way we do know is 10, if we didn't realize that and try to simplify the square root down, we will get the square root of 2 times 2 times 5 times 5. We make the square root and we start pulling out pairs. We can pull out a 2, we can pull out a 5. So there's nothing left on the inside of the square root. So actually you don't need the square root anymore. It's just 2 times 5, which is 10. So that is correct. Now there is, technically, you can think there's still being a 1 there. The square root of 1 though is 1, and multiplying by 1 doesn't do anything. So you can just think of it as if the square root gets emptied out and there's nothing left in, you don't need the square root anymore. And the square root of 1 is just 1. Okay, couple of quick examples. 75 can be simplified into 25 times 3. So 5, 5, and 3. Square root of 3 times 5 times 5. And we can pull out a set of 5s, and we're left with the 3 inside. if we do simplified, or not simplified, the method 2, square root of 75 is the square root of 25 times 3. Square root of 25 is 5, giving us 5 square roots of 3. 80. 80 is 8 times 10. 8, of course, is 4 times 2, 2 being prime. 10 is 2 times 5, both of which are prime. The 4 goes down into a couple of 2's. So the square root of 80 is the square root of 2 times 2 times 2 times 2 times 5. 2, 2, 2, 2, 2, and 5. Okay. We can pull out a 2 and another 2. And there's a 5 left over inside. 2 times 2, of course, is 4. So we get 4 square roots of 5. You can also realize the square root of 80. 80 is 16 times 5. 16, square root of 16 is 4. We get 4 square roots of 5. That's a 5, not an 8. One downside to this is that you are not likely to have your square roots of, or your multiples of 16 memorized. Method 2 is pretty fast when it works, but you need to know the multiples of your perfect squares. Knowing the multiples of 4 and 9 are pretty nice, but 16, not so nice. 25 is not bad. 36, you're not likely to know the multiples of 36. Okay, let's go over a couple more examples here. First, doing the method 1. 27 is 3 times 9. 9 is 3 times 3. This is 5 times the square root of 3 times 3 times 3. I'm going to copy down the 5 in the square root. I can pull out a set of 3's. That's 3 times 5, not 35. And there's a 3 left inside. 3 times 5 is 15. I get 15 square roots of 3. Now for method 2, 5 square roots of 27. 27 is 9 times 3. Square root of 9 is 3. 5 times 3 is 15. I get 15 square roots of 3. Same answer. Okay. 7 square roots of 30. 30 is 3 times 10. 3 is prime. 10 is 2 times 5. So this is 7 square roots of 2 times 3 times 5. There are no pairs for me to pull out, so I will just have to remultiply what's inside, and I get 7 square roots of 30. It doesn't reduce. Now, if you use method 2, the square root of 30, 4 doesn't go into 30, 9 doesn't go into 30, neither does 16. None of the squares smaller than 30 go into it, so it will not reduce any further. Okay, quick preview on your assignment. On number 1, you are going to be simplifying square roots 8 times. On number 2, you are using the Pythagorean theorem to find the missing length of the triangle. But once you know that length, you are to give it as a simplified square root, not as an approximation as we've done before. Number 3, find the distance between 2 points, or length of a line segment. Number 4 is a review of finding a fraction from a decimal, changing a decimal to a fraction. Number 5, tell me which number set that belongs to. 6 is solving an equation with squares in this time. Number 7 is simplifying a square root, but it's a big number on the inside. And on number 8, find the length of x. You're going to need to use the Pythagorean theorem several times here. You can use this triangle and solve for that length. Once you know that length, you can move to the next triangle and then solve for that length. And then after knowing that, you can use the next triangle with the information we now know to solve for x. And then when you get the answer, you need to simplify that square root.